Today we're going to be talking about inductance. Inductance is an electrical quantity related to inductors. Inductance is an application of Lenz's law. Now, what is Lenz's law? Lenz's law states that an induced current will opposes a change in a circuit that causes the induced current. Now, a little bit more on that later. I like to think of it like this. It's a chain of events. If we have a circuit like this is our DC power source. This is a resistor. And this is our inductor. Then we can observe the effects of inductance. Now remember that this is the positive terminal, this is negative, and conventional current will flow in this direction. What happens if the resistance of this resistor changes? What happens if it increases? So, a change in resistance will cause a change in current. That's pretty standard. A change in current will then cause a change in magnetic field, or B, and a change in magnetic field will cause a change in magnetic flux. This whole process of cause and effect gives us an induced voltage, or EMF, inside of our inductor. Now let's break it down with some equations. V is equal to IR. B is equal to U naught, or mu naught, IN over L. And last but not least, magnetic flux is equal to this. Okay, now we said we increased the resistance here in the circuit. So if resistance increases and we have a set battery voltage, that means that I, or current, has to decrease. If I decreases, that means that B also has to decrease, because these two are constants right here. So if I decreases, B decreases. Last but not least, if B decreases and A, which means area, is a constant, that means that magnetic flux also has to decrease. And this is a very important thing in this video. When magnetic flux changes, that's what causes our EMF. And in case you were wondering, magnetic flux is fairly simple. It means it is the measurement of the total magnetic field that passes perpendicularly through a given surface area. So if this was our surface area right here, and the magnetic field B was passing perpendicularly to it, like this, then to get our magnetic flux, all we would have to do is multiply B times the surface area, which is what we have here. But if the magnetic field is passing through at an angle, then you have to do a little bit of trig in order to figure out what the magnetic flux is. Anyway, the important part is that magnetic flux, when it's changing, is going to cause an EMF, or voltage, inside of our inductor. So this is something that you need to star. If you don't get anything else out of this video, I want you to understand this, that inductors resist or oppose changes in current. One more time. Inductors resist changes in current. Now let's use an example. We said before that resistance was changing, but let's just consider what's happening here with the inductor. Let's say this is our inductor. If current is flowing to the right in this direction, and it changes, that will cause this whole slew of events to occur, and we'll get an EMF, or induced voltage, inside of our conductor, or inductor. If I, or current, increases, that means that the change in current is happening to the right. This will oppose that, by creating an EMF that pushes in the opposite direction. This is interesting though, because if we put up a different example, if I is already going to the right and it decreases, that means that the change is not to the right, but to the left. Even though it's still moving to the right, the net change in current is to the left. So that causes the EMF to push in the opposite direction. I draw it like this because it's acting as if it were a power source. It's creating a voltage that's going to continue pushing in this direction so that current continues moving. In other words, it's resisting the change in current. One more example. If current is moving to the left and it increases, think about what would happen inside of the inductor. Which way would be your induced voltage? Because it's increasing this direction to the left, it needs to oppose that. So it would push to the right. And this is just shorthand notation for a power source, because it's acting as if it were a fake power source, resisting the change in current. Current will still increase in this direction if it needs to increase, but the inductor is going to make it a much more difficult process. Let's move on. So what have we been talking about? We've been talking about inductors which resist change in current. I'm going to write that down one more time. Remember, this is our key point in this video. Inductors resist or oppose changes in current. And this word oppose comes from Lenz's law, if you remember at the beginning of the video. We can represent changes in current like this. D for change of I, current, over changes in time. This shows us the rate of change of current. We can also set this equal to opposite induced voltage over L. L is an odd symbol in this equation. It is not length or anything like that. It symbolizes inductance. So L is the inductance of our inductor. Let's say the change in current is very quick, like 0 amps to 100 amps in 1 second. Just an example. If this whole left term is large, that means that this term also has to be large. So our induced voltage, or EMF, is going to be pretty large. If we change the inductance, however, by adding or subtracting loops to our coil, and all an inductor really is a series of loops, then we're going to affect the EMF inside of our inductor. This is applicable. If we want to achieve a large EMF, we have to modify the inductance of our inductor. Now let's do some rearranging. A common way to see this equation is like this. E is equal to negative L di dt. I just rearranged it algebraically. This is how you're going to see it, and in many cases, this is how you're going to solve problems. If it asks you for the induced voltage inside of an inductor, then you just plug in the inductance of that inductor and the rate of change of your current. I like to rearrange it and solve for L so that we can look at the units for inductance. This way, L is equal to negative E over di dt. And that is very interesting because we can look at the units for each one of these. Induced voltage is just a voltage, so it's in terms of V. Change in current is in terms of A for amp, and change in T is seconds. We give this whole term voltage, or volts per amps per second, the name Henry. So inductance of your inductor is measured in terms of henries. How is this useful? If I have a 5 Henry inductor, I will induce 5 volts for every 1 amp per second change. Let me write that down. a 5 Henry inductor is going to induce 5 volts for every 1 amp per second change. Now let's do an example problem. Inductors can be used to increase a voltage for a short period of time. Take a look at this circuit. As soon as the switch closes to this top side, right here, current begins increasing. Let's fill in the values. If this is a 25 volt power source, and this first resistor is 5 ohms, and this is 20 ohms, then we can solve the problem now that we have the values. The current is going to gradually increase because we have an inductor here. This is going to resist change. It's not going to be very instantaneous as soon as we close the circuit. Instead, this is going to oppose the change of current. So current starts flowing this way from the positive to the negative terminal, and this is going to oppose that by pushing back. However, eventually, you're going to build up current to its max value, and we can calculate that with the simple equation V is equal to IR. We have V, 25, and we have R, 5 ohms. Now all we have to do is solve for I. So in this case, it's very simple. I is going to equal 5 amps. So eventually, this is going to build up to 5 amps. At that point, there is going to be no more induced voltage inside of our inductor. And that's because the EMF is only present when you have a change in current. Remember before, inductors resist or oppose changes in current. But if our current is constant, then we're not going to have any EMF inside of our inductor. Now let's observe what happens when we flip the switch to this end. So we don't have this here anymore. Now we can ignore what's going on here. We know that initially we're going to have current flowing through our inductor this way. Because of that, we're going to have a voltage in this part of the circuit. And the reason why is because even though we don't have a power source, there is going to be a change in current. It wants to degrade. In other words, it wants to go from what it was, 5 amps, to 0. As it's doing that, though, it's going to create a voltage. And instantaneously, we can calculate that voltage or EMF inside of the inductor using the same equation. V is equal to IR. And the reason why is because for 1 split second, this I right here is going to be 5 amps. So voltage is equal to 5 amps times the resistance in the new circuit, which is 20 amps, or 20 ohms. And that gives us 100 volts. So look at that. We went from 25 volts to 100 volts just by flipping a switch. That's what makes inductors useful.